Hello everyone, I'm Wei He from Shandong University. The title of my paper is Enhanced Deep Residual Shrinkage Network with the Channel Estimation in RIS Communication System. Now, I will present my paper in the following 6 aspects: Introduction, System Model, Classic Channel Estimators, EDRSN-based channel estimation, Simulation results, and conclusion. Here is my introduction of my paper. Configurable intelligent surface, composed of a large number of passive components, can significantly save hardware cost and energy. However, its channel estimation is challenging since RIS commonly operates as a passive reflecting device and can't acquire the channel state information independently. In this paper, a data-driven approach for achieving highly accuracy channel estimation in RIS-assisted multi-user system is proposed. First, the channel estimation problem is modeled as a residual noise cancellation problem, and then the channel matrix with noise is obtained by a scale-least square channel estimation. Finally, an enhanced deep residual shrinkage network (EDRSN) is designed to reduce the noise and further improve the accuracy of channel estimation. Then we talk about the system model of our work. In this paper, time division duplex model is considered. Thus, uplink and downlink channels become reciprocal. RIS-assisted multi-user system as shown in Figure 1, and we can see here. RIS is equipped with N reflecting elements. Base station has N R receiving antennas, and here exists K single antenna users. HD, here is HD, represents the channel matrix of user to base station, and H denotes the channel matrix of user to RIS, and HB is the channel matrix of RIS to base station. We consider the passive RIS in this paper. Therefore, the RIS counter separately estimate the channel matrix H and HB. The objective of our work is to estimate the cascaded channel matrix Hj equal Hb, diag H and Hd. We assume that the RIS may generate D equal n plus 1 different phase shift modes when performing the channel estimation. The received pilot signal at base station in the this phase shift mode can be expressed as equation 1 and the YD. Due to the orthogonality between parallel sequence, we can rewrite the received signal in the this phase shift module as equation 2, and we can get the HDK. The received signal in all phase shift modes can be expressed as the equation 3. So we can get the YK equal HKP plus V. We will talk about the classical channel estimators. First, we will introduce least square channel estimation. Least square, we can call it LS, is designed according to the least square criterion with non-reflecting phase matrix P and the received signal YK. The channel matrix estimated by LS algorithm can be denoted by equation 4. So we can get the HKLS, and we can get the channel estimation error JLS as equation 5. Next, we will introduce SLS channel estimation. As we all know, LS estimation is very sensitive to noise, and the estimation performance may decrease dramatically with the decrease of SNR. SLS estimation can further reduce the mean square error (MSE) by allowing for bias. Based on analysis of LS estimation, the channel estimation errors of SLS estimation is given by equation 6. So we can see SLS is based on LS. When gamma equal gamma 0, the MSE of the channel estimation is minimal. The channel matrix estimated by SLS estimation can be written as equation 7. So we can get the HKSLS. And we can also get the channel estimation error JSLS as the equation 8. So we can see the JLS is greater than JSLS. So the SLS channel estimation is better than LS. And this part is our work. We design a network called EDRSN, means Enhanced Residual Shrinkage Network. In this section, the channel estimation in RIS-assisted multi-user system can be modeled as a residual noise cancellation problem, and we propose an EDRSN-based channel estimation scheme to input the noise feature extraction and cancellation by introducing soft refreshing hold and convolutional block attention module. We can call it CBAM. In the following, the EDRSN scheme is described in the terms of residual network, CBAM, and soft threshold. First is residual network. As we can see in figure 2, the structure of the residual network is shown. So Fx is the pre-summing network mapping, and the Hx is the input of the post-summing network mapping. The identity mapping can effectively alleviate the problem of gradient disappearance and performance degradation. Next is convolutional block attention module, so the CBAM. In the subsection, we further improve the residual deep reshrinkage network by introducing the CBAM shown in figure 3. CBAM is a lightweight attention model and can improve the model performance with low complexity. CBAM connects channel and spatial attention. So we can see here, the green one is the channel attention, and the purple, second one is the spatial attention, which can attach importance to key feature and ignore irrelevant features such as noise feature. Finally, we introduce soft threshold. As shown in figure 4, the key of soft threshold is to obtain a threshold value to eliminate non-significant features. We can obtain the threshold value alpha, that is the average value of normalized input feature x, by the operation shown in figure 4. And this is the operation. First is JEP and FC, or this one. Thus, threshold value is obtained by this module is the average of normalized input feature x. So we can get the conclusion that threshold can distinguish the main and the irrelevant features by setting the irrelevant features to be 0. Here is our network, EDRSN. We designed the EDRSN as a modification of the residual network ResNet, and it consists of one input layer and one residual shrinkage model with CBAM as shown in figure 5. So we can see, we first put the input YK and P and HK into SLS estimation to obtain the rough channel estimation results HKSLS. This one, HKLSS. And we put the HKLSS and the real channel matrix HK. HK is the real channel matrix to the EDRSN as the input data and the label. At last, the EDRSN optimizes the network parameters by means of a movement estimation gradient descent algorithm to make the predicted channel matrix HK EDRSN. This one is the predicted channel matrix is more close to HK. That means it's more close to the real matrix. And in this section, we provide the simulation results of the proposed EDRSN channel estimation in RIS-assisted multi-user system. We assume that base station has NR equal 8 receiving antennas, and there are K equal 8 users, each with a single transmitter antenna in the uplink scenario. Besides, RIS is equipped with N equal 32 reflected element, and the simulation parameters of EDRSN scheme are shown in table 1. So we can see the RIS element and the number of our user. This is how we set the learning rate to and the activation functions, loss functions, and optimizer. Let's look at the simulation results. The NMSE performance of the proposed EDRSN scheme, LS estimations, SLS algorithm, and the LMMSE scheme is shown in Figure 6. We find the EDRSN scheme, the blue one, outperformed the traditional LS, SLS, and LMMSE estimations because the EDRSN scheme is a nonlinear estimation that can learn the channel features and improve the NMSE performance. In addition, the EDRSN outperforms the convolutional scheme, especially in the case of low SNR. As we can see, in low SNR, the EDRSN is much better than the traditional one. That's because it can get more accurate channel metrics to eliminate the signal noise at the receiver. In Figure 7, we investigate the NMSE performance of the proposed EDRSN scheme and their different region factors at SNR equal 5 dB. And the values of the region factor kappa, this is the region factor kappa, affect the degree of refrequency selecting films, which in turn influences the channel states. So we can observe that LS and SLS estimation schemes are not affected by the variant of region factor kappa. This is because when LS and SLS scheme are appropriate for arbitrary frequency selective filling channels. In addition, since the EDRSN module is trained at kappa equal 10 dB, so we train the EDRSN scheme in 10 dB. It is seen that the NMSE performance of the EDRSN scheme decreases when kappa is not greater than 10 dB, due to the fact that the channel estimate it's the channel state of RIS to base station links becomes worse with small kappa. However, the proposed scheme still outperforms the LS and SLS scheme, and its estimation accuracy becomes better as kappa increased. Kappa increased, the performance is better. Therefore, when the channel estimation changes, the proposed EDRSN scheme can still estimate the channel matrix with high accuracy. And the last figure is Figure 8. The NMSE performance of the proposed EDRSN scheme and the convolutional LS estimations is tested in Figure 8 with different number of reflecting elements, N equal 32 and 64. And we can see that the channel estimations become, we can see that the channel metrics become more sparse as the N increases. So the NMSE performance of the EDRSN scheme at N equal 64 is better than that at N at 32. The 64 is better. Besides, the EDRSN scheme is superior to the convolutional LS scheme at both N equal 32 and N equal 64, which will demonstrates the superiority of EDRSN scheme with different N. And last is our conclusion. In this paper, we proposed an EDRSN channel estimation scheme based on SLS algorithm, where the SLS algorithm considers the impact of the noise on channel estimation to improve the channel pre-estimation accuracy. In addition, CBAM and soft threshold are introduced into the residual network to further extract the channel features and eliminate the noise. Simulation results demonstrate that the EDRSN scheme is more accurate compared with the other convolutional channel estimation scheme. And the convolutional channel estimation scheme is LS, SLS, and LMMSE. And we think we will make further research. Our further research may focus on the design of lightweight networks to reduce the complexity while maintain the accuracy of our channel estimation. So our further research object is to design a lightweight network. And this is my presentation. Thank you very much.